Hello, and welcome back for our second topic, which is psychophysics. I see that my Zoom updated between my last recording, so hopefully everything is working the same. A little bit of a change in where controls are. Well, the second topic that I want to cover is psychophysics here. Now, I covered in the first topic here, I broke it out into 4 videos, what I consider to be the general introduction to the sensation and perception topic and what I call the problems of perception. And we kind of tackled some of the core theoretical challenges that we're really faced with when it comes to understanding uh, how perception works. And this now is a little different because it is quite a bit more technical and is focused on this narrow little field called psychophysics, which is covered in fairly good detail in chapter 1 of your book. And one thing that I really did not want to do is spend a lot of these lectures repeating things that you can already read about and learn about sufficiently in the book. This is why I don't have, as I had mentioned in my introductory syllabus day video, I'm not going to have dozens and dozens of hours of lecture recordings like I otherwise could do in principle. So why am I doing this topic here? There's 2 reasons, really. Number one, I think that because this particular content can be just a little bit technical, you might benefit from getting it from 2 different perspectives here. One, of course, is the chapter 1 version of it. Then you get my version of it, and together maybe this content will be quite a bit more sensible to you. But number 2, one of the brief paper assignments is to do a mini experiment, an informal, off-the-cuff kind of sensation or perception experiment. And in the introductory syllabus video, I had raised a couple of different options for ideas for studies that you could do. And one of them was something in the ballpark of like various different degrees of sugar solution, and see whether or not people rate it as being maybe more or less sweet, depending on whether you add food coloring to it or you look at other sort of individual difference variables, age and things of that nature. So one of the implications of that is that if you're going to do an experiment where you ask people to judge the intensity of the sweetness of sugar solution or any other stimulus that you might try to put together, you're using a psychophysical technique. And I thought it would probably be useful for me to ensure that we could kind of cover the basics of how to do some of those basic psychophysical techniques here. So let's get into it before I just keep on talking for too long. As I always say, I try to keep these videos as brief as I can, and that almost always fails. But nevertheless, I am trying to not make you watch, dozens of hours of videos. You should be familiar with this diagram already. I used this one in the first set of notes as a schematic of the sensation-mediated theory of perception. And I want to revisit this because one thing I want to do is I want to try to couch the concept of psychophysics within this particular theory. So just as a really quick review, again, the idea is that there are things out there in the world, the distal stimulus, in this case, there's a tree, which then information about that distal stimulus is carried to our sensory organs. In this case, that would be light reflecting from the tree, enters into your eye. And the activation of the receptors in the eye then cause visual sensations, ideas of color and brightness, let's say, which then must somehow be converted, interpreted, decoded, etc., by the brain into a coherent and meaningful perception so that I know and recognize that I'm looking at a tree and I construct my mental representation of the tree out of those internal sensations. So we've talked about this before. Now, the obvious thing we had previously talked about is the relationship between my mental representation of reality and actual external reality. And we got into some of the little philosophical concerns there of skepticism and so forth. And as it turns out, curiously enough, most perceptual research has little regard for this question, despite how important it may be. The one place it comes up is on the last slide of the introductory notes when I talked about Gibson's ecological approach, because Gibson in particular is very concerned about this question, about the degree to which perception informs about some kind of reality. But in traditional research, we tend to start really with this question, right? So of course, there's three arrows on this slide, right, on this diagram. One is the arrow that describes light, and certainly, of course, it's relevant when talking about vision to describe how light reflects from a surface and then is gathered by an eye and how the eye works. In fact, that's coming up in the next couple of chapters, is a great deal of detail about light and eyes and optics and the further advanced neural processing of the information coming from the eye back to the brain. So there's a lot of stuff to cover in that that kind of arrow that goes from the tree to the eye, as well as the eye itself. And so we're going to do that. There's certainly, of course, the third arrow that takes us from sensation to perception. Is something that we talked about quite a bit in the first set of notes, talking about, say, inferential theories like Helmholtz's unconscious inference or Bayesian predictive processing and so forth. And so that's really an introduction to the idea. There's most of the book really is all about different theories for what kinds of things can happen to get us from sensation to perception. But that middle arrow actually represents the beginning of sensory research. And some could say even the very beginnings of experimental psychology. I am a fan of how the textbook authors write about how Fechner essentially invents experimental psychology, despite the fact that most history of psych books will argue that Wundt was the first. And that's only because Wundt was the first to actually use the term experimental psychology and created a laboratory that he called the Institute for Experimental Psychology. But decades before that, Fechner was doing psychophysical research, believing that he was maybe uncovering some mathematical connection between the physical and the psychological, and perhaps maybe solving the mind-body dualism problem. I don't think he succeeded in that regard philosophically, but he did launch this attempt to understand the psychophysical world functions, right? So that's what that term means. It's a portmanteau of psychological and physical. And so what we're thinking about here are the physical stimuli that can stimulate all of the various receptors, and then the psychological or sensation-related response here, right? So we've been mentioning this before, that light can be described in terms of two characteristics or dimensions. It can vary in its intensity or photon flux, which we think determines the brightness of a visual stimulus. And light can also vary in its wavelength, and we think that determines the perceived color of a stimulus. Sounds can vary in their intensity in terms of the amplitude of the pressure wave, which may correspond to perceived loudness. They can also vary in their frequency, which is just the inverse of wavelength, and that would presumably correspond to the pitch of a tone. Different types of chemicals that we ingest might cause different kinds of primary taste sensations. So something that is acidic may taste sour. Different kinds of sugar molecules, and there's different kinds of sugar molecules, but they're all relatively similar from a molecular perspective. I don't think we need to go review chemistry here, but any of these molecules or compounds that end with the OSE sound, like glucose, maltose, fructose, lactose, and so on. They're all very similar molecules, and they all taste sweet because they activate a similar class of receptors here. So it seems like different kinds of categories of chemicals there will activate different types of taste receptors, giving us, some sweet, sour, salty, bitter, savory primary taste components and so forth. And the intensity of the taste would be a function of the essentially the concentration density of the solution, right? Like I suggested before, if you dissolve a few grams of sugar into a certain amount of water, then you're going to have a certain amount of parts per million there in terms of the concentration or gravity of the solution, right? And you could just dissolve more and more and more and create something almost like a syrup, which will increasingly taste more and more sweet, right? And so one thing that we might be interested in understanding here is, all right, if the intensity of the light corresponds to brightness, what we can do is we can measure using physical instruments, we can measure the photonic flux of the light. We can measure the wavelength of the light. We can measure the amplitude of a sound pressure wave. We can measure the frequency of a pressure wave. So all of these things that are on the left-hand side of those equal signs are things that can be physically measured with various instruments, right? But the things on the right-hand side cannot be physically measured with instruments because these are more subjective sensory responses. But what we can do is we can ask people to provide some sort of an estimate or judgment of that sensory response. All right, so to tell me if I play a sound that has a particular amplitude level that I can measure in physical terms, I want you to try to report subjectively how loud is it. And then if I change the intensity levels by some amount, I want to know how much of a change have you experienced, right? And maybe one thing I want to do is I want to map out the objective change in the sound amplitude level in proportional terms, perhaps. Maybe I increased the amplitude by 10% or 20%. So does that mean that the subjective loudness of that sound has also increased by the exact same proportional change? That if I increase the amplitude by 10%, do you perceive the subjective loudness as increasing by 10%, or is it some other number? Well, we can do that kind of research, and we can map out these relationships. And that's exactly what Fechner had in mind here with inventing psychophysics, or what we call psychophysical modeling, which is in fact about modeling that relationship, mathematically modeling the relationship between the physical stimulus intensity and the psychological intensity of the response. We call this modeling because we can generate, as you can see here, a graph, right, a curve, and there will be an equation that describes this curve. I have a form of that equation on the slide here using the Greek letter psi, psi for the psychological response, and the Greek letter phi, phi, for the physical stimulus. And so what we would say is that the psychological response is some function f of the physical stimulus. And so what we want to understand here is, what is that function, right? And this is a mathematical function that converts the physical intensity into a psychological intensity. And that, of course, is exactly what your sensory organs are doing, right? That the receptors in the eye respond to these properties of light and convert that into these sensations. The receptors in your ear respond to some properties of pressure waves and convert that into sensations. And the goal of psychophysical research then is to figure out what are these, what we might call psychophysical transfer functions, right? Transferring the physical into the psychological. Technical word for that is called transduction, because what happens is that the energy of, say, electromagnetic radiation is converted into nerve energy, and corresponding to the nerve energy is then some sort of sensory response, a visual sensation, an auditory sensation, so forth. So here I'm talking about it in terms of pitch, but it could be any of those stimulus dimensions that we've been talking about. One way to do this research, though, is to start by talking about a threshold, right? What is and why is that important? Well, so this example that I talked about before of, let's say I increase the sound amplitude by 10%, and I want to know to what extent we have changed the subjective loudness. Have we increased it by 10% as well? Well, that's a difficult question to ask people, right? It's a little bit weird if you think about it, for me to try to judge whether a sound has increased its loudness by 10% or a factor of 0.1 is what that would really be. It's kind of weird, right? It's possible to ask this question, but maybe we could try to be a little bit more concrete with the questions that we ask subjects so that we don't have to ask them to come up with such weird estimates. Oh, I think that was an increase of 0.1 or an increase of 0.15 compared to the previous stimulus, right? So what we want to do is to give them simpler judgments to make, which is simply something like a yes or no response. And the yes or no response would come from the fact that we're going to ask them a simple question such as, can you hear this sound? Yes or no? Can you feel this pressure on your skin? Yes or no? Can you taste any amount of sugar in this water? Imagine I give you just a little glass of pure distilled water, pure H2O. You shouldn't taste anything. But if you put a small amount of sugar and dissolve it in there, if you just put one sugar crystal in there, what you're going to find is that you ask a person if they taste any sweetness, and most likely they'll say no, because that's really not enough to really create a detectable level of sweetness. So we're going to keep adding more sugar until somebody says, okay, yes, now I can taste something, right? So these are simple yes, no questions. And this is called, the way I just described this, is the absolute threshold, the weakest stimulus intensity that a person can detect. So if I'm doing this taste perception experiment, I want to know how much sugar needs to be dissolved in a certain amount of water. What's the concentration of the solution before it is detectably sweet. If I'm doing a hearing experiment, I want to know what's the minimum amplitude of a sound wave that I need to present before a person says, yes, I can hear. That's, of course, exactly what you go through if you have a hearing test, an audiogram, right? Is that, just to make sure that all your hearing thresholds are normal, meaning that we want to know that you can hear sounds at the appropriate level, right? If you have some sort of hearing loss, then that means that your thresholds are higher than normal because the sound has to be a little bit louder objectively, physically, before you actually hear it. By the way, the term threshold, why do we use that term? Well, imagine the idea, the threshold is another word that we oftentimes think about as that little strip on the bottom of the door, front door to your house. And the idea is that you have to step up over it in order to walk through the doorway. And so there would be some amount of energy you have to exert to step over the threshold to enter into the house. Well, it's this kind of metaphorical thinking that led to this term being used for psychophysics as well, because we think that the stimulus has to have some minimum amount of energy to step up over the threshold of consciousness to enter into your mind and activate the receptors and therefore create an actual detectable sensory response that you're aware of, right? So we can measure the absolute threshold. We can also measure what's called a difference threshold. So let's go back to that example I said before about changing the loudness of a sound by 10%. Well, I'm not going to ask our subject to tell me what percentage it has changed. I just want to ask someone, can you detect any change? Right. So if I increase the loudness of the sound by 10%, physically, objectively, I'm just going to ask my subject, do you hear anything different? Did that noticeably change? And maybe the answer is no. So what I might discover is that maybe I have to increase the loudness by 20% before my subject will say, oh yeah, now that sounds louder than it did before. And this is called a difference threshold, right? And that summarizes this concept of saying, how much does the stimulus have to change before I notice the change, right? So the idea is that we're starting, in a way, the absolute threshold is like a difference threshold relative to zero. So if we start with no stimulus intensity, the question is, how much do I have to increase it above zero before a person notices a change from zero, which is that they can detect it at all, right? That's our absolute threshold, the weakest stimulus that you can detect relative to zero. But then above that, once we have a stimulus that's already detectable, that's above the absolute threshold. Now what I want to do is I want to change it somehow. I want to either increase or decrease its intensity, and I want to determine how much it takes for you to notice that change. The abbreviation J and D that's on the slide here is part of that. That's short for the just noticeable difference. And that's a really, I think, common sense way of thinking about this. This is the term Fechner originally used. It's just how much does the stimulus have to be different before you notice that? That is, what is the just noticeable difference? Now, one of the things that we need to notice here is that this function is not as clear cut as we might expect it to be, right? So the expectation is here on the left that our threshold might look like a stair-step function, right? And that's what we see there is if we're below the threshold, I'm simply going to ask you to say, can you hear this sound? And you're going to say no. And then I increase it a little bit. So we see we're moving to the right on the x-axis, and you still say no. And then I increase it a little bit more. So we're still moving to the right on the x-axis, the actual physical intensity. And you still say no. But now what I do is I bump it up one more time, and I've hit your threshold. And so then we would expect that your judgments would shift dramatically from no to yes. And that as I continue to increase the intensity beyond that point, now we are at 100% yes responding, right? So we are essentially at 0% yes responding until we hit the threshold, and then it just jumps drastically up to 100%. And that's called a stair-step function, because it's just jumping up discretely and suddenly from 0% to 100% detection, right? Reality, it doesn't look like this, however. What is frequently the case is that human sensory performance is quite messy, quite variable, and somewhat unpredictable. And so our functions look very much more like the curve here on the right-hand side, in which a stimulus that is above threshold is not always detected 100% of the time, but is sometimes detected maybe 80% of the time. Sometimes a stimulus that's very, very faint is detected maybe 5 or 10% of the time. So is that above threshold because I can detect it sometimes, 10% of the time? And we have to realize here that when we do these kinds of experiments, you really have to do lots and lots of trials. All right, so I'm going to present a stimulus of a very weak sound, and I'm going to then present a stimulus of another sound that's maybe a little bit weaker or a little bit louder. Maybe it's a random ordering of different intensities. And I'm going to just continue to ask you over and over again, tell me yes or no. Can you hear this? Yes or no? And sometimes, let's say I present a particular stimulus 10 times, and 9 out of 10 times you say no, but that one time you said yes. So how do I treat that particular response? Do I treat that as evidence that you can technically hear that sound? Well, yes, technically you can hear it because you said yes and it was really there. So should I determine that that is your threshold because you were able to detect that stimulus one time out of 10? Well, the rule of thumb that we use is that we are not going to do that. What we want to do is we're going to pick the halfway point up the curve, which is the 50% mark. And so any stimulus that is detected below 50% of the time is going to be considered below threshold. And any stimulus that's detected more than 50% of the time will now be considered above threshold. So we're going to define then that any stimulus that's detected 50% of the time exactly as your actual absolute threshold. But the same also would apply to a difference threshold. So if you notice the change 10% of the time, then we will say that that's not yet officially a sufficient change to be considered a difference threshold or J and D. You have to be able to notice the change in the stimulus at least half the time for that to be considered a J and D. So this implies that there, as I had emphasized, that there's some variability, messiness to human performance. Anyone with even the slightest little exposure to psychology research should know that that's true. But what we're seeing here is that, a lot of times when we think about human psychology research, we're measuring more abstract and complex variables that are harder to define, like personality traits or IQ. Obviously, that's going to be pretty variable. But In this case, we're trying to do something that's really objective, just measuring whether you can or cannot detect a stimulus. And even in this case, there's quite a bit of variability. So one thing we need to think about, though, are what are the methods used to get at our thresholds. And I think now is a good point to go ahead and stop, so that way you can maybe digest everything that I've kind of covered already about just the general idea of thresholds. And then we will go into the actual research of how to perform these psychophysical experiments and measure the threshold.